Awesome. So before I start on my slides, I just wanted to very quickly answer one of the questions we had from the previous presentation. I think what was asked was, what is the expected amount of nitrogen fixation from different crops, especially cover crops? So it's a kind of a serendipity moment. I was actually reviewing some work that is coming out from USDA Dairy Forage. These fact sheets are not out officially yet. I was looking through them, but they actually had a compilation of nitrogen fixation from different cover crops and other legumes. So, for example, for alfalfa in one growing season, the amount of nitrogen fixation can go between 50 and 300 pounds of nitrogen per acre. For red clover, 50 to 250. Hairy vetch, 50 pounds to 150 pounds of nitrogen per acre. Bird's foot trefoil, 30 to 200. So a couple of things about this range, all of them, for all these different legumes, the range is quite wide. The reason for that is that takes into account on the lower end, typically when these legumes are being grown with other crops, like in a grass legume mixture. And also just for context, of course, this nitrogen fixation, when we think about it per acre, it's very strongly associated with just the amount of production. So if you have a very productive legume that is just producing a lot of biomass, typically the nitrogen fixation per acre also increases. And of course, we can get into more details later in the Q&A, but that depends on a number of different factors, including just nutrient availability, soil pH. And if someone has more questions about it, we have some efforts looking at that. We don't have results yet, but if you're curious, you can ask me again at the Q&A section. All right. Okay. So now going to my presentation. Today, I'm focusing on the effect of traffic on alfalfa production. So the first thing that I wanted to talk about is, why is it that we are so concerned with the effect of traffic? So you'll notice most of my presentations, I typically add a long list of names to it. These are all the individuals that have been involved with these efforts. So I want to make sure I recognize my postdoc, Beatriz Bizzuti, who is leading a lot of these efforts. Scott Newell, who's part of this call, has been an integral part of these projects as well. And then Brian Lug, Francisco Arriaga, Mark Rentz, all UW Extension professors, and then John Grabbett and Heathcliff Brade from USDA Dairy Forage, again, great partners of ours. So, concerns with traffic. We do know that alfalfa production, just a typical year of production, requires a lot of different mechanized operations. So just typically an alfalfa field requires more mechanized operations than a lot of the other crops. So that makes it more susceptible to any kind of negative effect that traffic may have on a field. And we estimate that around 50% of a productive alfalfa field will receive traffic or will traffic at least once during the growing season. Where is this number coming from? This data comes from work developed by Brian Luck and in collaboration with Francisco, where they actually added a GPS tracker to each piece of equipment that was running in a commercial alfalfa at a dairy. Okay, a commercial alfalfa production field at a dairy. So on the top panel here, you can see each one of these colorful lines is showing a different piece of equipment that was tracked. And then here on the purple, those are the areas of the field that have not received any wheel traffic. So this purple area amounts to just around 50%. And again, I just want to emphasize that that is at least one event of traffic on top of that alfalfa. It could be more events here. The reason why we are concerned about wheel traffic, it's twofold. So that the number one, we're concerned about that effect on the soil, specifically soil compaction. And I know that the previous presenters already set me up to talk about this, because the concern we have is if we have more traffic, we can reduce that bulk density of the soil and reduce the macropores, the larger pores that help with water infiltration. So we can have reduced water infiltration. We can have reduced oxygen air diffusion through that soil profile, which is needed for the plants to develop well. And we can also, depending on how much that soil is compacted, it can actually be a physical impediment for root development of our crop. And if the roots are not developed well, not only the structure of the plant is compromised, but also just the ability of absorb water and nutrients as well. The second reason why we are concerned about wheel traffic is the effect on the plants. So we do know that depending on timing, and I'm going to talk about that more in just a little bit, but as different types of equipment drive on top of plants, we can damage tissue. And when we're thinking about alfalfa, we're particularly concerned on damaging all of those growing points and new shoots that are coming out from the crown. But we're also concerned about increased disease occurrence, particularly crown rot. So there is this study, for example, in Minnesota, where the researchers were looking at 4 different alfalfa varieties, and they ranged in terms of susceptibility to disease from more to less resistant. This was done over 2 subsequent years at 2 locations, so 4 location year experiment, where they harvested the alfalfa and then they imposed traffic on top of it 48 hours after that event. So the alfalfa was cut. That means that some of those new shoots were coming out and to some extent more exposed, and then they were hit by traffic. And those data points were compared to the same alfalfa types but without the traffic. So we're basically trying to compare in a field, an area that was trafficked versus an area that didn't receive any wheel traffic. And they measured 3 responses: forage harvested, plant counts, and also a crown rot. And what they found is that areas that received traffic had a reduction in both production and plant counts of 13 to 16%, and that also increased the occurrence of crown rot. So those damages to the plant are a big driver of why we are looking and investigating this a little bit more. So I'm going to show results from 2 studies here. The first one, again, this is data from collaborative efforts with Francisco Arriaga and Brian Luck. We are looking at the effect of traffic imposed on alfalfa fields from typical management practices. So this was a study that was imposed, it was started in 2019, and then those fields were followed for 2020 and 2021. So a total of 3 years receiving this traffic stress. So again, we always have plots that have not received any traffic so that we can compare what is happening on traffic-stressed areas compared to areas that do not receive stress from traffic in the same location. So if it was a dry year or a wet year and that changed production of alfalfa, we can kind of tease out what is coming from the traffic stress compared to other types of stress that have happened during that growing season. And we're doing 4 treatments. We have 3 passes and 5 passes for silage or for hay production. The biggest difference between silage and hay here, for silage, so that there were fields of alfalfa, they were harvested, and then the traffic stress was imposed 24 to 26 hours after harvest. Now, when we're evaluating this for hay, that traffic stress was imposed 48 to 72 hours later. So what that is basically what we're trying to look is if we allow more time of regrow between that harvest and the traffic stress, what is happening? All right. So there are two questions that we can answer with this experiment. The first one is, what is the effect of time in terms of traffic stress in production? So these graphs here are all going to have a similar format. We have the forage harvested on the y-axis right here. This is the total in that growing season. And then we have the no traffic in black here, and then the two traffic treatments in green. So in 2019, so that is the seeding year, what happened? We see that the traffic and the silage treatments were similar. All right, meaning that that earlier traffic really didn't make a difference in production. However, when we look at hay production, we see a decrease of 24% in forage mass. All right, so that later traffic stress reduced significantly the production of alfalfa. In the following year, so these are the same fields that were imposed in 2019, were established in 2019. They were followed in 2020, receiving the same treatments. The no traffic treatments, so the areas that didn't have any stress due to wheel traffic, had an intermediary amount of biomass compared to silage and hay. But then again, hay production, so that later time in traffic stress reduced production in around 14%. A different way for us to look at it is to look at those 4 harvest events on that second year, the first fully established year, which is what we're showing here. This is the no traffic biomass on each one of those harvests. We can kind of see this is very typical of alfalfa production, right? We start with greater biomass production, and there is a reduction over time. So how does that compare to hay? We can see here that the green dots that are showing the hay production, very similar behavior, but that line that is kind of representing what is happening during the growing season has a much steeper angle. What that means is that that reduction is more intense over time when we are using the fields for hay on the trafficked areas compared to areas that are not receiving traffic. So the second question we were curious about was, is it going to be different if we traffic areas 3 or 5 times? So is there a cumulative effect of these traffic events? So again, forage accumulation is here on the y-axis. What we can see is when there is no traffic, there is more production than in areas that receive traffic, but whether they receive that stress 3 or 5 times, it wasn't different. And again, this reduction is around 15%, and this was also on the seeding year. All right. So the take-home messages from this first study are that wheel traffic from typical operations, they do reduce alfalfa production, and that greater interval between harvest and traffic that allows for that regrow results in greater damage to the shoots. So just imagine if you see those nice new shoots that have this really tender tissue, if they receive that impact, that stress, that will likely destroy or at least really reduce the growth of those shoots. So that's basically what we're seeing here. Interestingly enough, on the third year of this study, so in 2021, there was no treatment effect. So whether areas were trafficked or not, production was similar. So there seems to be some level of adaptation or plasticity of alfalfa fields over time. So, and also frequency of traffic didn't really have a consistent effect, meaning that whether you traffic an area more or less, at least on this study, we didn't see an effect. All right, so it was whether it was 3 or 5 passes, it was equally negative. Okay, so now changing gears just a little bit. This is still going to be about traffic, but in a different production system, which is the interseeded system, where we're interseeding alfalfa into corn. Very quickly going over how this system works. So the very typical rotation that we have here in Wisconsin between corn and alfalfa is on year one. We are planting that corn for silage, we're harvesting it, and then next year we plant alfalfa, right? So in this interseeded system, what we are proposing is planting alfalfa with corn. So as we harvest, we have an alfalfa field in the fall. So we're harvesting corn silage. We are allowing a little bit of time for that alfalfa to establish during the fall time. And we start the second year with production that is basically equivalent to a fully established alfalfa field. So what we're proposing here is we basically skip that first year of alfalfa production that tends to be quite low. And we are starting to harvest that alfalfa once it's already at full production. So on that first year, we're just harvesting the corn. Now, there are some things that are needed for this system to work well. One of them is that we do need to have lower corn seeding rates. So we need a lower corn population in these fields. This is basically to make sure that we're going to allow light and airflow underneath the corn canopy for as long as we can to really help that alfalfa develop over time. Alfalfa, on the other hand, is seeded at typical rates. However, we do know a couple of things that are required for this alfalfa to really establish well. One of them is not all alfalfa cultivars varieties are well adapted to this system. We already tested a lot of them. So there are some that just work really well. And we're also still working on selecting some genetic material that will really thrive in this system. So we already have some that work extremely well. But what we know this is that we can, there is space to improve it even more. All right. The second thing is we do know that fungicide treatment is really important for alfalfa survival and good establishment. So again, going to the point where alfalfa is underneath that corn canopy, there's not a lot of airflow, is warm, there's a lot of moisture. It's really an environment where diseases can thrive. So fungicide application is really important in any year, in a typical year, in a wet year. In really wet years, we also found that applying a plant growth regulator on the alfalfa really helps. This regulator is going to help alfalfa direct some of that energy, that growth to below ground biomass. And that really helps with persistence of the alfalfa stand. So on regular dry years, that doesn't make a big of a difference. But for example, in years like the one we had this year, where the spring was super wet, that is definitely something that helps the alfalfa establishment. All right. Okay. So if you're very curious about this system, you can look at the World Dairy Expo YouTube channel. There is a talk by my colleague, Mark Rentz, where he talks a lot about just the typical management practices associated with this. And we also have these links where we have a number of fact sheets with information. So again, some of the varieties do really well in the system, and we tested it, so there is a list in that fact sheet where you can look at which ones, if you're wanting to try it, which ones will work well. Now, just going over what we've seen in terms of production for this system, I'm going to show data from two locations in large plots. So all these graphs, the next two slides that I'm going to share, they have the same format. So we're always comparing this interseeded system to a typical system. So corn on the first year, followed by alfalfa on the second year. So we're seeing here data from a large demonstration plot that was established in Arlington in 2022. So this is corn established, we had to apply herbicide, and then alfalfa was established in the spring. And this was the production of corn silage on that first year. And then on the second year, this was the production of alfalfa, around 11 tons of dry matter per acre. That final value right there at the bottom, that's the sum of biomass from the first and from the second year. So now looking at how that compares to the interseeded system. So these plots were established side by side, all right? So we're looking at two treatments again. Both of them have like a nice recommended fungicide application standard. And then one of them has the plant regulator, growth regulator as well, all right? So again, they were established, corn and alfalfa were established together. I want to get your attention to the number of management, the number of passes we had in each year. So this system is more complex. It requires you're managing two crops at the same time. So it does require more management tasks associated with the system. And we can then look at what was the production of corn silage on that year. So we can see that in this year, there was no yield drag for corn silage. Typically, like looking at data from several years and locations, the average yield drag is around 10%. All right, so this was unusually a higher or like very comparable yield compared to corn being grown alone. But the expectation is to have around a 10% yield drag on average. However, when we look at year two, you can see that you really do start with a fully established alfalfa stand. So when we compare total biomass from both years, so corn silage and alfalfa, we see an increase of 25 to 30% in total biomass production compared to the corn followed by alfalfa. Very similar results at Lancaster. Again, so the typical system on this first column, and then the corn interseeded with alfalfa on this columns 2 and 3. And again, we see a production increase of around 30%. All right. And all right. Let's see. Okay, so coming back to traffic, why are we looking at traffic on these interseeded systems as well? We already went over this. Alfalfa has a lot of mechanized tasks associated with production and management. But when we're looking at this corn interseeded system, we have an additional management practices associated with corn production. And we are particularly concerned about the heavy equipment that runs over these fields during the corn harvest activities. So this is something that producers brought out to us. Some of them had tried this interseeded system, but in wet years or wet areas where the fields were established, sometimes the alfalfa didn't bounce back very well after corn harvest. So this is something that we were interested to understand, like what is the effect, what is happening in terms of traffic stress on the interseeded systems. So as good researchers that we are, we established an experiment at Arlington. What you're looking here is this is an interseeded system again. So we started this past year. So this is the corn phase. So corn and alfalfa were established together, but this is the year where we're harvesting corn. So these are the treatments that we are looking at. We are looking at no traffic. So again, we're always comparing what is happening in traffic areas compared to a no traffic area. All right. And we're looking at the effect of chopper, truck, tractor, and then combination of chopper and truck and chopper and tractor. So basically what we did is we harvested all of these plots with a really light plot harvester. So the no traffic all the way to the chopper and tractor, they were harvested with this very light plot harvester. And then 24 hours later, we impose traffic with real equipment that would be utilized during the corn harvest. And today I'm going to focus the results in the no traffic and the chopper and truck. So just to exemplify and illustrate what we were looking at, this is how the plots looked in the no traffic treatment. So all you can see is a very minimal effect of that small plot harvester. You can see here still the stalks of corn are still up. You can see some alfalfa plants here. One thing that I'm going to talk about in just a little bit is you can see these two circles. These are PVC bases that we use to collect soil respiration. I'm going to talk about it in just a minute. But you can see that we have two in between the corn lines. So there are 4 alfalfa lines here. And one of these bases is positioned in between the alfalfa lines. So really looking at the effect of traffic in soil respiration on the soil only. And one of them is positioned right at the center of the alfalfa line. So we're looking at soil and plant, how they respond to traffic in terms of soil respiration. So here is the chopper and truck treatment. You can see that there was not one corn stalk that survived up. And the alfalfa plants are really, really smashed close to the soil level here. And we collected data of soil respiration and cover evaluation. And just as a side note, we know that this was maybe a little bit more of a stressful year for this system, at least for the alfalfa section or the alfalfa phase of the system, because the spring was so wet. But also it was relatively dry at the time of traffic. So our expectation is that the effect of traffic wasn't as bad as if this had been a really wet fall when we were harvesting and therefore imposing our treatments. So these are the same treatments 7 days after traffic. Again, we received 1.7 inches of rain in between traffic imposition and this picture. So no traffic, looks like it has a lot more plants compared to the chopper and truck. And again, the same thing at 10 days after. So why is it that we're looking at soil respiration? So this is kind of a proxy for measuring soil health. Basically, if there is CO2 production, that means that the microorganisms and the plants are growing, right? So that's what soil respiration measures. It measures the root respiration of plants, as well as respiration from microorganisms in the soil. All right. So basically, again, when we were measuring soil respiration on the alfalfa row, we were looking at soil and plant respiration. And when we were doing that in between the alfalfa rows, we're just looking at soil respiration. All right, and this is the device that we use to measure. So let's look at the results. So again, in black here on your left, you're looking at no traffic, and on the right, you're looking at traffic treatments. What we saw that is in between the rows, so focus on soil respiration, there was very limited effect. They were statistically similar, meaning that they were basically not different, okay? Now, when we look at the soil respiration on the row, what we see is first that if there is a plant there, soil respiration is greater, of course, because we have plant and soil compared to just soil. But also, what we saw is that there is a significant effect of traffic on soil respiration when we're looking at that plant plus soil respiration. That reduction is in just around 20%. So this suggests not that soil is not important, but just that the effect on the plants is the bigger driver of this reduction in soil respiration. So the plants are really responding to the stress of traffic by reducing growth, reducing then soil respiration. Now, looking at the same treatments in terms of cover in the fall. So this was a visual evaluation of green cover in each one of those plots. And what we found is that, again, there was a statistical difference where no traffic had around 40%, 43% cover, and that was significantly reduced in areas that received traffic from the chopper and the truck combined. That was a reduction to around 35%. So as again, good researchers that we are, these were the treatments again that we were evaluating during the corn phase, that first phase. But that was not sufficient for us. So we actually had twice as many plots we needed because this next year, this coming growing season, 2025, we are going to follow those same plots again during the alfalfa phase and see how they're going to react if they receive no traffic stress compared to traffic stress from the harvest. And basically what we're trying to do is if we compare here on this year too, we want to see are the plants going to recover at all? Is that worse traffic the first time, is that sufficient to really damage the alfalfa stand and have a long-term effect? And also, even if we don't traffic during the corn phase, if we start stressing that alfalfa stand with the harvest events during the alfalfa phase, how much of a reduction of biomass, if any, we're going to find. We're also going to establish the exact same experiment again next year. And that's just so that we are able to better capture year-to-year variability. So next year, we're again going to have a corn phase data set and a complete system year 1, year 2 data set. So we're very excited we get to run these experiments so we can answer more of these questions. So this is what I had for us today. I'll stay for the Q&A, but happy to transfer now to Dr. Harkirat Kaur.